Pretty good crowd. Got a panel today that is going to be gripping. We're going to talk about Remote PHY 2.0 and Remote PHY distributed schedulers. And we are joined by two absolute thought leaders in the marketplace. I want to welcome everybody to the session. A little bit of housekeeping. Please set your mobile devices to silent. We'll dispense with a lot of the upfront protocol. We got a very rich set of information to share with you today. So we're going to go 20 to 25 minutes for each presenter, and then we'll do questions and answers at the end of the session. So with that, I'm Sean Welch, and I look after the cable access business for Cisco. We're joined by Pawel, Sowinski, who's also with Cisco Systems, and Tong, who is also with Cisco Systems. And this is not a conspiracy. We're here to share with us, with the marketplace, the broader evolution of Remote PHY and where we see the marketplace going. And we got lots of great, technical content to share with everybody today. So with that, I will move on to our first speaker. I'm going to introduce him. His name is Pawel Sowinski. He's a software architect for the Cisco Cable Access Business Unit in the CTO's office, where he works on next generation technologies and architectures for their adoption by the industry. For many of you who are involved in the Remote PHY committees, you probably have interacted with Pawel in lots of different settings in terms of modifications and enhancements and edits to the specification. He's contributed to the development of Cable Labs DOCSIS 3.1 specs. He's primary author of the Remote PHY specification itself. He holds a master's in science and computer science and a master's in science in electrical engineering from the Technical University of Gdansk, Poland. He is the publisher of several technical papers and authored multiple patents related to core cable technologies and in the area of general data communications. Please join me in welcoming Pawel to the stage.
Thank you, Sean.
You bet.
Not sure if this works.
You have to use a touchpad.
Use the touchpad.
Okay.
That little arrow thing right there. Yeah, let me see if I can help.
One second. Yeah.
There you go.
Okay. Good afternoon. I'm here to present a paper that I wrote along with my colleagues on the next steps for Remote PHY technology. So first I'd like to thank my colleagues, Tong, who's going to present her paper next, and Andy Smith, who I think is present at the booth at this time. His duty prevented him from participating in the panel. Right, so let's first take a short look at the opportunity, at the landscape of Remote PHY technology. On one side, Remote PHY has achieved some stability island because it has complete technical maturity. It's functionally complete, and Cable Labs is actually planning to conclude the current effort for standardization of Remote PHY. On the other hand, it has also achieved a phase of wide-scale deployments. Multiple operators around the world are adopting Remote PHY. The number of subscribers, paying subscribers receiving service for Remote PHY can be counted in at least hundreds of thousands. I don't have precise and recent data. I know that every week, at least in our company, we see tens of thousands of subscribers being added to the MSO networks that are served by our equipment. So maybe the number is actually counting now in millions. On the other hand, there are new emerging requirements, such as low latency, expanded spectrum, and the forever desire to reduce the costs, as well as there are some shifts in technology. The CCAPs are virtualized. Essentially, every piece of networking equipment is being virtualized, and the operators are focusing on network automation. So those four corners create a perfect opportunity to reassess current technical solutions and plan for next steps. Now, what is Remote PHY 2.0? I think I need to start with an announcement. I was talking to John Schnorr yesterday. He's a technical lead for distributed CCAP architectures at Cable Labs. He told me that Cable Labs has agreed to start a Remote PHY 2.0 project, and we need to aggressively start developing a schedule for it. Unfortunately, or fortunately, it was a joke. Or fake news.
I can neither confirm nor deny that.
Remote PHY 2.0 is just a working title. It's a convenient label we have chosen to apply to the new set of features that we presented in a paper that might be changed in the future. The paper presents in detail four architectural options for Remote PHY technology. The first one is a cloud-friendly control plane. Second is model-driven telemetry. Then we have remote upstream bandwidth scheduler. And then we also talk about certain improvements to Remote PHY data plane. The paper refers to the existing Remote PHY specification and devices that implement those specifications as Remote PHY 1.0 or 1.0 in short. And our goal is to start or initiate an industry discussion about the future of Remote PHY technology. So we think that all those features are worthy to package together. There are good technical, compelling reasons for moving ahead with them on an individual basis. Together they form Remote PHY 2.0, but this is intended as starting discussion so that the entire industry can participate. So let's start with the cloud-friendly control. Let's first describe the Remote PHY control paradigm. As many of you may know, Remote PHY is a concept where the PHY components of the CCAP are taken out of the same system and put in a separate system located in a different place. Those systems are called CCAP core, that's the CCAP without the PHY, and the RPD that implements the PHY components of the CCAP. Between them, there is a set of networking connections. Those connections, in this setup, the CCAP core and the RPD are in a master-slave relationship. CCAP core controls the RPD and acts as a master. The RPD is a slave and takes control of the CCAP core. With CCAP core decomposition, which is division of function of the CCAP core into independent systems, the RPD must serve multiple masters. Serving multiple masters is a hard discipline. This was by far the most difficult part of the specification to ensure the system worked. The RPD system worked well with multiple CCAP cores. Each of the CCAP cores controls a set of independent resources organized in sort of silos. Let's discuss the technical details of Remote PHY control protocol, the 1.0 control protocol. It uses TCP and IPsec for transport and security. It uses general control protocol for messaging. It relies on RCP for data models and encoding. These data models and encodings are defined in DOCSIS-like TLVs. But unlike in DOCSIS, where those TLVs are fully custom to the functions that derive, the Remote PHY Control Protocol 1.0 uses the FCAPS framework. FCAPS stands for Faults Configuration, Accounting, Performance, and Security, which are the foundations of all network management protocols. In terms of performance, RCP 1.0 has transfers a moderate amount of information. Mostly during configuration, we see spikes of volumes per RPD, but after that, the amount of control information exchange is very small. However, the protocol has tight real-time requirements. In worst case, for processing of a UCV message, the RPD is required to do that in 50 milliseconds. That's in order to limit the amount of dead time on the upstream spectrum. Now let's discuss, let's assess the RCP 1.0. It has a number of pros. It has been proven to allow effective replication of ICCAP features in a DCA specification. It's based on open cable app specifications. Those specifications are open to any vendor who's willing to sign cable apps agreements, and they are available for free download from cable apps website. It supports very efficient encoding. On the con side, RCP 1.0 is very unique. It's only implemented in one application field and fairly narrow if you compare it to the depth of the ocean of the networking applications. It currently does not provide, there's no open source code system for the RCP. And therefore, there are few development and test tools. The uniqueness is the Achilles heel of Remote PHY, because the uniqueness translates into a set of business issues, such as difficulty in testing and implementation and integration with other systems, especially cloud-based systems. And that those set of issues also translate into a higher OPEX and longer development cycles. It's one of the reasons why Remote PHY took 5 years from the start of the project to the point where the systems are being deployed at scale. Not the only reason. So the key of the proposal is to replace GCP and RCP with modern YANG-based protocol. YANG is the foundation of cloud-native APIs and automation. YANG stands for yet another generation network management protocol. It's a well-established standard for network APIs and automation. It has a very wide deployment field. It's not only used to manage physical network elements and virtualized network elements, but also in aeronautic, automotive, military, and many other applications. YANG is based on IETF standards, RFCs 6020 and 7950. 7950 actually is called YANG version 1.1, and that's what's implemented in most applications right now. It's supported by a set of mature development and test ecosystems that can be easily integrated with cloud systems. As an historical fact, Yang was first introduced into cable app specifications, into DOCSIS, about 10 years ago when we developed the first CCAP specifications. It was used by the CCAP to provide a common configuration models. And again, Yang is a key enabler of network automation. The methodology for transitioning from RCP towards Yang-based protocol includes 3 elements. The first element is translation of the RPD data models from RCP into Yang. Those RPD models are uncomplicated. They are simply hierarchical trees with very few cross dependencies, but they are quite voluminous. The RCP portion of the specification of the Remote PHY specification occupies about 240 pages out of the 400-page document. The second step is to eliminate from the protocol stringent real-time requirements. For example, we propose to remove processing of DOCSIS, certain DOCSIS messages from the control protocol and require that an RPD processes them in band, just like the cable modem. You know, in theory, a device that's many times more expensive and many times more complicated than a cable modem should be able to support similar performance requirements. So we don't think there are technical reasons, there may be implementation reasons why those DOCSIS messages are being processed as a in-control protocol. And then the third step is to select a transport protocol. There are 3 protocols that I'm showing on the slide. They can be organized in a parallel stack. Many networking devices support all 3 of those. The paper leaves the question of selection of a protocol to future discussion. It's, you know, we can either go for a low-cost solution where we will standardize on a single protocol, or perhaps require that RPD supports all protocols, and the operators will be able to choose them to fit to the network. Now let's discuss backwards compatibility. Obviously, the CCAP cores can support both protocols. It's a standard in the networking device world where a master device can talk to both newer and older devices. Can the RPD also support backwards compatible operation with 1.0 CCAP cores? We think that the answer to the question is yes. With precise data model translation, it should be possible to have an RPD with a stack similar to what we are showing on the slide, where the RCP operates on top of the Yang models, and the RPD can simultaneously talk to 1.0 cores and 2.0 cores. And that feature allows with a transition from 1.0 to 2.0, because that allows the operators to incrementally upgrade the CCAP cores in the system from 1.0 to 2.0, and perhaps even leave some of the CCAP cores at 1.0 level because they provide lower value functions and maybe they are slated for obsolescence. So an operator could upgrade the principal core, the core that has certain central functions, to 2.0 protocol to fully take advantage of the benefits of the 2.0 protocol. At the same time, upgrade the DOCSIS core, which will also benefit from 2.0. But in order to not increase the cost of the transition, the operators can leave the video core and maybe out-of-band core at the 1.0 level, and the RPD can talk to these systems using 1.0 or 2.0, depending on the operator's choice. 5 minutes. Right. We're almost done with the cloud-friendly control plane. The second feature on the list is or second architectural option is the model-driven telemetry. This is where the entire network industry is going. It's transitioning from query-based SNMP towards push model and streaming data. So once we have the young models on the RPD, it's really a no-brainer to implement a streaming telemetry out of it. The streaming telemetry framework requires two systems. One is the device that produces the data, the other is the device that collects the data, so the collector. Operational data is pushed from the device to external collector. The collection is based on a subscription. It's essentially a contract between the device and the collector. The subscription includes an arbitrary set of young models that can be monitored by the collector. So if you have the entire network management API of the device in young, you can choose any component of it and stream it over the telemetry. It's a simple yet extremely powerful methodology for delivery of metric data from where it's created to where it's acted on. It's broadly supported by commercial solutions and open sources. You can take the data out of the RPD, throw it on a Kafka bus, deliver it to as many places that are willing to subscribe to the Kafka bus. Model-driven telemetry will become a foundation for modern health monitoring systems. That's one way in which you can increase the reliability of your network and reduce the cost associated with maintaining it. I'm going to yield the Remote PHY, Remote Optimum Scheduler to Tong, because we're running out of time. And then let's discuss the data plane improvements. Several operators came back to us and told us that they would like to run Remote PHY along with other traffic in the network. But the problem is that the data plane protocol, L2TP v3, is not well suited for operation in best effort networks. The solution that we're proposing as part of Remote PHY 2.0 is to apply well-proven MPLS traffic engineering technology, including segment routing, as a method of solving the problem. There are two options explained in the paper. One is a PSP running directly over MPLS, where we eliminate the L2TP stack from underneath it. And the second option, preferred by Andy, who's the author of that section, is to run, Andy prefers the option of running MPLS, PSP directly over MPLS. The second option is to run MPLS as an outer traffic envelope over L2TP, and that solution has the benefit of being backwards compatible. How much time do we have? 2 minutes. So, by applying MPLS principles, the operators will be able to traffic engineer the networks in order to meet Remote PHY requirements and also run other traffic over the same network. A CCAP core and the RPD are both will be both capable of applying MPLS labels obtained from BGP route reflector and managing the QoS of the network through SDN-like infrastructure. So in conclusion, Remote PHY 2.0 presents a set of architectural options. The whole is greater than the sum of its parts. It's an opening for a conversation about the next generation of Remote PHY technology, which with 4 options explained in the paper and 4 other options mentioned in the paper. We internally at Cisco have about a dozen of those architectural features that we are considering. Each of the architectural options solves an important business problem for cable operators, And as a result, Remote PHY 2.0 offers a premise of a better network performance with cloud-native APIs, with lower OpEx, and improved feature velocity. Thank you.
Thank you very much, Pawel. I would encourage everybody to read the technical content. The paper is awesome, and lots of detail in there. Please engage with Pawel independently with your thoughts and modifications and edifications along the way. Our next speaker is Tong Lu. She's principal engineer in the CTO office at Cisco. And she's responsible for CMTS and CCAP software architectural work, research and development, and emerging DOCSIS technologies and standards. She represents Cisco and has contributed to the standards developments, cable labs, including Remote PHY, full duplex DOCSIS, low latency DOCSIS, and low latency XHAL. Her current areas of interest include low latency DOCSIS scheduling and real-time computing in the cloud environment. Tong has over 19 years of experience in product development in cable industry, covering a range of CMTS, CCAP, and Remote PHY products and technologies. Dr. Lu holds a PhD in computer and electrical engineering from Boston University and a master's in science in electrical and communications engineering from Tsinghua. Did I say that right? I'm sorry. Tsinghua University. Tong has published over a dozen journals and conference papers and patents filed or issued by the U.S. Patent and Trade Office. Please join me in welcoming Tong Lu.
That was Tsinghua University.
There we go. I knew I butchered it, so.
So let me how to change that. Just test my voice here. I'm a soft speaker, so make sure everybody at the end can hear me all right? Okay, sum up, thank you. My topic today is R-PHY with Remote Upstream Scheduler. That topic Pawel skipped because he ran out of time. Hopefully I will do a better job explaining the topic. Before I start, I want to briefly introduce the co-author of this paper as well, John Chapman. John had this remote upstream scheduler idea way back at the start of R-PHY development. And he kept this idea in his back pocket just in case it is needed by the market. And we think now is the time to bring it forward and make it available to benefit R-PHY for low latency purpose. So with that, let's get started. Quickly, agenda today, that's a thought process I'm going to follow for my talk. So first, what is the market requirement? Why do we need to do this? Second, where is the latency bottleneck in the R-PHY system today? And we take a look, try to pinpoint that particular problem. And then how to remove the bottleneck for low latency purpose. And finally, we're going to take a look at some preliminary lab result and summarize the discussion with certain takeaways. All right, low latency market requirement. Low latency is a new buzzword in cable industry today. It's so hot that we hear it almost every day. Why? Because it's crucial to compete with fiber, and also it's crucial to tap into the wells for the emerging gaming market, and also to open up HFC to be a valid candidate to support the mobile XHAL market. The list going on, there's a bunch of new cool latency-based applications. So whenever there's a strong market requirement, it will encourage technology innovations. So here's a low latency solution set we've been seeing in the cable industry today. First, LDEQM, which stands for Low Latency DOCSIS Active Queue Management. So this technology basically tackles the buffer bloat problem and preparing DOCSIS to be ready for a new TCP congestion control algorithm called the TCP prog or L4S. There's also enhancement to DOCSIS protocol itself. So in the latest MOPI spec, you can notice there's new requirement for something called a proactive granting service, or PGS. And there's also a requirement to reduce current 2 millisecond map interval to 1 millisecond interval in order to reduce the request grant latency. There's another innovative technology called pipelining used by the Low Latency XHAL Committee. Specifically, we call that BWR and the DTP. Basically, what it does is try to synchronize the mobile scheduler with DOCSIS scheduler so that the DOCSIS network doesn't add additional delay on top of mobile access. Now the fourth one. Here's our talk, our contribution here. R-PHY with remote scheduler. So what we're doing here is try to find an optimum location for the upstream scheduler so we can reduce low latency in DAA R-PHY architecture. So by doing that, we're introducing a new flavor of R-PHY, and we call that low latency R-PHY. We get into the same name terminology, we call that LLR. So as Pawel mentioned, this LLR will be included in the next generation R-PHY. We call that R-PHY 2.0 feature set. However, if it's desired, this LLR can also be implemented on top of R-PHY 1.0, which is a legacy R-PHY, what we have today with proper software update. Before I jump too far, let's first take a look at what we have today. Today, in the integrated CCAP, we use a centralized scheduler. Because the scheduler is located at the core, the request grant has to traverse the HFC network back and forth in order to get a scheduling decision back to the cable modem for the cable modem to send the data upstream. So, but luckily, because we have 2 millisecond maps that we have been using, under these 2 millisecond maps, if the HFC distance is within 100 miles, it turns out the HFC round-trip propagation delay doesn't do any harm, and we'll explain why on the slide after this. And R-PHY 1.0, which is current R-PHY, simply copied over this centralized scheduling scheme. Why? Because it works, and the HFC delay, it doesn't make any difference in terms of the latency, because for most cases, RPD is placed within the 100-mile range from the core, and everybody's equipment is using 2 millisecond maps. So in this situation, where you put your scheduler doesn't really matter because SYN doesn't do any harm. Now let's take a deeper look to see what is magic about the 2 millisecond map and 100 miles. I want you to remember these two parameters because later on I want to change them. So this is really two sides of the coin. First, you look at the green bars over there, right? So that's, if you're looking at it from a request grant protocol point of view, data coming into the cable modem send a bandwidth request using a map. So for every map being used, there's another map waiting in line, waiting next door, which is already built. So the earliest time for a grant available for this particular, the purple color request is 2 maps away. So we are using 2 millisecond maps, that's equivalent to the earliest grant will be 4 milliseconds away. So and then with additional 1 millisecond for the request processing and transmission time, we're talking about a minimum 5 millisecond request grant delay, simply because of the protocol reasons. Now, this 5 millisecond turns out to give a sort of a timing budget in terms of how long your requests and grant messages can be can take, how much time it can take for it to be processed at the cable modem, transported through the SYN network to the CMTS, and CMTS process it, generate a grant, and propagate it down to the cable modem through the delay. So it turns out if the SYN network distance is within 100 miles, all the little factors add up together is within 5 milliseconds. So look at the orange bars, which indicating the SYN delay. If you remove it, it doesn't do any good because the 5 millisecond request grant protocol delay, that one is the dominating factor. That one is the bottleneck. So that's why centralized scheduling works under this operational condition, 2 millisecond maps and 100 miles. Now, if one of these two parameters changes, the centralized scheduling will no longer be optimal. Let's look at why. First case. Come on.
Use the button above.
Now, if I run out of time because this Sean don't believe me. So the first case is I have, okay now, thank you. So first case is I have this request grant delay remains the same, 2 millisecond map, nothing changed over there. What it changes, the R-PHY is deployed over 100-mile distance, so it's a long range. So in this situation, you can see the request grant transport and processing delay is crawling beyond this 5 millisecond boundary over there. And this transport delay becomes a dominating factor. So in this situation, cutting down the sync delay does directly help reduce the overall upstream latency. So that's case one. Let's see case two. Case two is now we keep the sync delay the same. How about we reduce the map interval from 2 milliseconds to 1 millisecond? Remember, this is one of the technologies recently appeared, reduce the map interval to 2 milliseconds to 1 millisecond, right? So by doing that, the request grant product delay is shrink by half. In this situation, the sync delay has nowhere to head, right? This guy, the bottom one, become a dominating factor. So in this situation, cutting the sync delay is also very meaningful to reduce overall upstream scheduling latency. So this is case two. And because it's two cases, that's why we bring into the remote upstream scheduler concept. So how to do it? So-called remote upstream scheduler is we put a scheduler at the RPD itself. Let that guy spin fast to turn around the request and generate a grant right back to the cable modem. So the request and the grant doesn't have to traverse through the SYN network all the way to the core. However, we still keep the scheduler at the core. Why we do that? Because there's a limited compute resource at the RPD. There's a power restrictions, there's a CPU resource constrictions, a memory restriction, all 9 yards of it. So we keep the scheduler at the core to take care of all those computation intensive, however, latency tolerant scheduling tasks. By doing this, we sort of best use the limited resource at the RPD to get the what is the word? Biggest bang for the buck, right? So, for this, we achieve low latency at a lower cost. So what that gave to you with the remote scheduler? That gave us a new DAA scenario we added to the DAA ecosystem. So the top two remote are the R-PHY scenarios. The bottom three are the FMA scenarios. The second one is we just added, right? So that is RPD with the most timing critical piece of software in the world, which is the upstream scheduler over there, right? So what that gave to you, it's low latency support over R-PHY architecture. And if you look at it far away, oh, wait a second, that is FMA Lite, right? Because it provides, it's equivalent to FMA in terms of upstream scheduling latency, however, at a much lower cost, because I don't need that much of CPU to run the entire MAC on the node, only a little bit to run my scheduler, right? So I can return the existing R-PHY interface in terms of a forwarding plan, control plan, and a management interface. So that's where I hope over there to introduce a low latency component to the RPD to support low latency, however, return R-PHY's low cost and efficiency over there. Now let's see how to do it. So in the low latency R-PHY, we call that LLR, right? In this LLR, what the scheduling model looks like, there's actually two schedulers. There's one scheduler lives in the core, we call that a core upstream scheduler. And there's one lives in the RPD, we call that RPD upstream scheduler. So the core upstream scheduler is a client or the controller. He oversees the latency requirement and overall resource constraint and resource distribution. So it will turn around to ask a remote scheduler, hey, I have a low latency service flow, please enable the request grant service right at the door. So the core scheduler will take care of the load balancing among the scheduler tasks. Collectively, this core scheduler and the remote scheduler, they will provide the DOCSIS upstream service for the higher layer MACs. For example, to ensure the quals, to ensure upstream SLAs, and to serve certain features, for example, ranging, probing, PNM, or full duplex sounding procedure, you name it, all the complicated applications who have scheduling need. So that's a core ops scheduler's responsibility. Now, in between the core ops upstream scheduler and the remote scheduler, there will be a new published APIs. That's a remote scheduling API that will be included in R-PHY 2.0, as Pawel previously mentioned, or added to the existing R-PHY 1.0 spec to make sure interoperability between different core vendors and RPD vendors. So let's cut the cheese over there. What kind of remote scheduling service we are talking about? We're talking about 3 main remote scheduling service. Number 1, remote request grant scheduling. When enabled, the bandwidth request coming from the upstream file will locally terminate at the local CPU at the RPD and generate a grant right over there. The remote request grant scheduling API will allow the core to provision a proper quals parameters so that remote scheduler knows how much bandwidth to give to a particular service flow. The second service in the service chain is remote map build service. The remote map build service is basically to translate a scheduling decision, for example, granting bytes, into a map encoding into a mini slots in this time and frequency domain as a results block, right? So this remote map builder has 2 potential clients. One is internally, the guy on the left, right, to serve the internal remote request grant scheduling module, or externally to serve the core serve the core upstream scheduler. Remember that there is still scheduling function taking care of those non-latency sensitive applications, for example, ranging probing, or any grant that doesn't need a bandwidth request, for example, UGS or PGS, those kind of things, right? So it will be remote map builder's functionality to translate those grant scheduling intention into actual map at ease. The third one is remote map UCD replication. As we all know, in a MAC domain, the map message may need to be carried on multiple primary downstream channels. This one, map UCD replication, used to be a core functionality. Guess what? The memory copy actually take a lot of CPU cycles. And also, those map messages need to traverse the SYN network, take a lot of network load as well, right? So by doing the remote map UCD replication, it alleviate the CPU load at the core as well as reduce latency sensitive map traffic through the SYN network as well. So these are the 3 service types that we're talking about when we're talking about remote scheduling service. Now, how's the UIP? What's UIP change? So the chart on the left is what we have for our UIP today, our sample remote. And the chart on the right is what we have for the UIP, our UIP adaptation to adapt to the remote scheduler framework. I lost my word over there. So what's the difference over here, right? So well, you can see on the left, there's a single upstream scheduler entity for the centralized scheduling. The chart on the left, which with the remote scheduler, you just split this single scheduling entity into 2 pieces. And same pseudoware from the PHY point of view, right? So you have a map pseudoware, request pseudoware, ranging and probing. The only difference is endpoint location changes. So the UIP map pseudoware and the UIP request pseudoware terminated as a remote scheduler for the chart on the right? So that's only different over there. So from PHY point of view, nothing changed. That PHY doesn't know whether the UIP is end on a remote scheduler or the core scheduler. So there's no PHY silicon impact. So the conclusion is our UIP can easily support the remote upstream scheduling structure. How about RDIP? So again, on the top is what we have today, RDIP. Now let's look at what happens to the in the LR situation. So again, what is changed over here? So on the top is what we have is because you have a core scheduler, the map and UCDs are injected into the PSP flow from the core. When you have a remote scheduler, the map and UCD are injected locally at the RPD. Same pseudoware, PSP flows, different map UCD, PSP flow injection point, no PHY silicon changes. So we're okay over there as well in terms of RDIP adaptation. Well, how about the remote scheduling APIs? Remember in the UIP structure, you split the scheduler to 2 pieces. In between runs this remote upstream scheduler APIs. So what we do is we can use existing API definition stack or utilize R-PHY 2.0 API definition stack. I mean, in terms of API, this is a very colorful picture, but you think about it, so-called API definition, only two area of task. First is you define the content, right? What do you want to say? So that is driven today is by the UML information model. We all know the UML information model in the spec. I mean, there's in the OSSI spec, right? And in the R-PHY 2.0, we're going to use young data model. So what's the difference between information model and data model? Data model is something you can compile. You can generate code. You can generate an API automatically right away. You don't need a bunch of principal engineers to write the spec, write the requirement in English manually, right? So that's the difference. That will definitely speed up the adaptation of the standard. So on top of the content of the API and all the upper layers, what they're doing, they just define a mechanism to transport the API from point A to point B in the network. So in that scenario, we need to worry about what network protocol you need to use, what is the encoding of the message, what kind of API will be formed based on those different things so that the code can code this, right? So there's in R-PHY 2.0, we have a bunch of different options. They give different performance in terms of the API speed conveying the messages, and that up to the further discussion once it goes to the Cable Lab Standard Committee. So I won't spend more time on that. So here is just to give a flavor in terms of what is upstream scheduler young data model looks like. I won't spend too much time already, I run out of time as well. So basically, we will add a new data module under the existing RPD operational configure model, right? So, and we will have one remote scheduler instance per MAC domain. Inside the MAC domain, we will have a data branch for each of the service tab. Remember, we have 3 services? So, and this is what the data tree looks like for remote request grant service. This is what it looks like for remote map building service. This is what it looks like for remote map UCD replication service. All right, what's the philosophy here? So philosophy for the remote scheduler to enable low latency R-PHY, the basic philosophy is to system-wide locality optimization. So we distribute the low latency scheduling to the RPDs, right? So to take care of the latency part. And then we centralize the computation complexity at the core. And we also provide a common scheduling platform for all the RPDs, taking care of the legacy guys, right? So we're backward compatible. So the ultimate goal is to optimize both latency and efficiency with certain vertical load balancing. So you can think about it as distributed computing with central control. We did some prototype of it. I want to, basically we add a scheduler container together with the RPD, and we compare the centralized scheduling with the remote scheduling. Here's what we have. See if I can get it. It's supposed to move. Did they move? So basically, the blue line is upstream latency without the remote upstream scheduler. The orange line is the one is upstream latency with remote upstream scheduling. So the difference is a SYN delay and the network jitter over there, right? So in the lab environment, there not too much SYN delay, but without upstream scheduler, we're talking about the upstream latency here 5 to 6 milliseconds with remote scheduler that pushing down to around 3 milliseconds. So you can see a lot latency differences over there. Okay, takeaways. LLR, remember what LLR stands for? Low latency remote PHY. So LLR is cost effective in reducing DOCSIS upstream latency. Why do we claim that? First, it's equivalent to FMA in upstream latency, but requires much less software and CPU resource as a node. Second, it eliminates latency-sensitive map traffic from SYN. Remember, we build a map at the RPD, we replicate map at RPD, no map traffic over the SYN. You don't have to do lease line for the map UCD traffic anymore. Third, a relaxed real-time requirement at the CCAP core, right? So, I mean, the scheduling decision can be made like UGS, PGS at service flow activation time. The scheduler at the core doesn't have to spin crazily to generate some decision every 1 millisecond or 2 milliseconds. So we make CCAP core lab a lot easier. Finally, no downstream PHY or upstream PHY silicon changes. Everything is software. Anything can be done in software and it's software, no silicon impact. Well, LR is backward compatible with R-PHY 1.0 and it's coming soon in R-PHY 2.0. If you have any questions, I will be at the booth. See me at the booth 1301. Thank you.
Thank you, Tong, for that thoughtful presentation. So we're going to open it up to the floor for questions and answers. Please step to the mic or stand up and shout out your question. Anybody got a question? Come on. All right. I'll go to my questions that I have. Okay, so Tong, to you. Why was Remote Scheduler not considered at the time of the initial Remote PHY development?
So as I mentioned, when John proposed this Remote PHY ideas, so he thought about it. And then there's a type, both business reasons and technical reasons why we didn't bring this remote scheduler at day one. So the business reason is the initial development, initial deployment of R-PHY 1.0 is simply to replace analog fiber with digital fiber. And so the operational environment is the same as ICCAP. And also by just putting the PHY component into the node, we'll sort of keep all the centralized, keep all the complexity centralized. And that's easy for both vendors and operators because we know how to manage the MAC, including the scheduler component. So that's from business point of view. I mean, with this, we allow to roll out the DA architecture as fast as possible, right? Just replace analog fiber with digital fiber. With that, we can enable the next stage of the evolution of the DA. From technical reason point of view, which I explained in the slide over there, is because under 2 millisecond maps, the request grant protocol delay covered us up, right? So that covered the up to 100 miles in distance. So under that protocol latency, there's no need to move the scheduler somewhere else. So if it's not broken, don't fix it to keep everything simple. Sorry for the long answer.
Great, thanks, Tom. All right, I did my part. I asked my question. Anybody got a question out there? Yes.
Would the current generation R-PHYs be able to upgrade it? Or perceive that the CPU advanced speeds so much that go to your generation?
I will repeat the question for everybody. Will current generation RPDs support this scheduling capability based upon the horsepower and capabilities available?
Yeah, sure. So right now, on the RPD, there's a CPU over there, right? So you need to run driver code. You need to run, some vendors using OpenRPD. Some vendor doesn't use it, but you have the all GCP protocol support, everything over there, right? So it depends on how much CPU horsepower left over there, right? So in Cisco, we make RPD, so we think that's enough horsepower to do something over there. And also for this, the beauty of this remote upstream scheduling is we can give it a fine resolution to enable it per channel, per service flow level. For example, if the leftover CPU power can only support build maps for a single channel, and then you can aggregate all the low latency service flows on that particular upstream channel, only build maps, do the remote request grant for that particular channel, and all the other channels, it can still, they're still scheduled centralized so that you can maximize your limited CPU resource for that a few low latency service flow or a few upstream channels to maximize latency, sort of focused feature in that sense.
Okay. Any other questions out there? Yes.
Are the MPLS data plane improvements, are those compatible with your IPv6 networks?
They should be.
Did
I
everybody
don't
hear
think
the
the
question?
paper describes any reasons why not. In fact, the paper describes the ability to run MPLS on its own and also run segment routing using MPLS.
Okay. Any other questions? All right, well, with that, I want to thank you for attending the session. Please take advantage of reading the papers in detail, and we'll give you 5 minutes to shift between classes. Thank you very much.